Good afternoon, ladies and gentlemen. Let me present to you our thesis project. We are Group 3, and we're going to present a cryptonic operating system supervised by Siemens and Dr. Mohamed Shalan. Me, Jana, Shalaby, and my colleagues will present this presentation, Mahmoud, Ziyad, Youssef, Ali, and Haggar. Let me quickly go through our table of contents today. First, we will state our problem and solution, and then we will discuss our system architecture, and then we will go discussing configurations as well as showing a demo and ending our presentation with a demo empowerment outcome. So for our thesis statement is basically to design a lightweight operating system, single core OSIC complement, and it should be portable OS that will provide the ability to do basic scheduling, as well as for security tasks and interrupts on the HSM.
Okay, so now I'm going to go over the problem that we solved, or rather the opportunity that we saw and how we went about solving. I'm sure we're all well aware of what is currently going on in the automotive market, where cars are shifting from using traditional engines to being more smart, more connected, and having more ECUs in their system. As you can see here, the global connected car market is expected to increase by 100 billion US dollars over the course of the next 10 years. That means that with each passing year, that network of cars is only going to get bigger and bigger. Now, with these advancements, however, comes new threats and challenges in the automotive industry, especially in the cybersecurity department. A study shows that from 2019 to 2022, there has been a 99% increase in the cybersecurity incidents. Now, this is most likely due to how aggressive the shift was in the industry and how we are adding more ECUs to the core each year. Now, these cybersecurity incidents can take various forms, like, for example, remote key exploitation, infotainment system attacks, or ransomware attacks. Solving these issues is crucial in order to maintain security in the automotive industry, especially if you want to one day thrive to adapt autonomous driving systems in our daily lives. So to combat this, the HSM was developed. The HSM is the main motivation behind our project. It is basically a piece of hardware that is responsible for doing cryptographic operations on the hardware level rather than the software level. Now, why is this good? Well, first of all, relying on the accelerators that the HSM provides is much faster in execution than doing them on using a software algorithm. This automatically qualifies the HSM to be used in most embedded environments, especially the automotive industry. Second of all, the HSM is extremely tamper-proof. It provides a safe and secure environment in order to do critical heavy operations like encryption and decryption of data, generating random numbers, keys, certificates, and performing hashing functions. Just to give you an idea of how secure the HSM is, if the HSM was able to find a breach in its system or finds out that the data has been corrupted, it will actually lock the HSM core and will delete its data forever. This is actually something we had to make sure we avoid while working on. So the problem that we are addressing is how developers interact with the HSM. Up until now, the main way that developers interact with the HSM, at least from the architectures that we've studied, is by a bridge channel between the host core and the HSM core. So if a developer wishes to invoke a single operation, he would have to send a message through that bridge to the HSM core. The HSM core would have to then perform the operation and then return back the message. Now, quite frankly, this is very unproductive. The developer will more than likely be constantly generating new keys, certificates, perform multiple hashing functions. So we want the developer to have a more hands-on and a more interactive experience with when developing code on the accelerators of the HSM core. So our solution to this is simple. We will flash our own operating system onto the HSM core. Now, what this does is that it provides a new way to interact with the HSM core, where now the developer can actually write custom code onto the HSM core, and he can predefine his own tasks to run on the HSM core. Now, the bridge is used only to invoke interrupts from the host core, and these interrupts, when triggered, can activate the respective task. When the task is finished, the HSM core can return the result back to the host core. This is very productive. It offers a neat environment for the developers that are working on the HSM core to develop more efficient solutions and software applications. Now, we've decided to adopt these two standards in our project. The AUTOSAR standards is the most widely used standard in the automotive industry, so it would be the most sensible option to adopt it in our project, since most applications that are built around it adopt the automotive industry. The OSIC standards stem out from the AUTOSAR standards, and they are basically provide the documentation on how to implement an OS for AUTOSAR applications. So we need to make needed to make sure that we strictly abide by the OSIC implementation for our OS to be standardized. We also want to make sure that our OS maintains these two characteristics. We want to make sure that our OS is portable, and by portable we mean that you don't have to you can just developers can port the OS to any HSM core. All they have to do is simply write the hardware portion of the code, and they can simply integrate it with our software code, and they will have their OS running. And as a matter of fact, it actually doesn't have to be ported onto an HSM core. It can actually be ported to any general purpose core, like the host, for example. We also want to make sure that our OS is lightweight. And when we say lightweight, I mean that goes hand in hand with it being portable. So we want to make sure that our OS doesn't sacrifice any of the speed or the safety or security requirements of the HSM core. So in order to do that, we had to pick out the features that we thought were crucial in building a minimal operating system in order to preserve it being lightweight and portable. And from the AUTOSAR specifications of building an OS, we decided that we will only build 60% of those specifications in order to maintain our OS being lightweight.
So our system integrates two distinct categories of functionalities, those defined by OSIC and custom developed functionalities. So we had to abide by the OSIC developed functionalities in order to form the foundation of our system. And we also had to introduce custom aspects in order to address our requirements. So let me introduce you to the OSIC defined features. First, we have task management, which handles task states and execution control. Next, we have execution control, which enables the developers to interact with the OS as a whole, which enables them to start or shut down the system. Next, we have resource management. It allows the developer to declare, obtain, or the resources of through the OSIC resource management system. And then we have the events. It empowers the developer to specify features that triggers tasks waiting for certain conditions. And then we have interrupts, which enables the developer to manage the responsiveness of the system through enabling or disabling interrupts. And finally, we have hooks, which empowers the developer to specify functions before and after task execution, OS boost, or error handling. And now let me introduce you to our task state diagram. So we have 4 main states, running, ready, suspended, and waiting. And in order a task to move from one state to another, we call certain APIs. So for example, we can call activate in order to change from a suspended state into a running state. And then we can call a schedule to move a ready state into a running state. And for the running state, to move back to the ready state, we can call schedule, and it can either also be terminated by calling terminate, or it can be moved back to the waiting state by calling wait event. And for a waiting event to move back to the ready state, we can call set event.
Now, moving on to our implementation and quick overview and an example for our scheduling. It's responsible for arranging the tasks together in descending order by their own priorities in the ready queue. For example, here, task 3 is in the running task because its priority is 10, and when it continues, it will activate task 4, which is priority 6, and it will be inserted in our ready queue and placed correctly in it. And then when we try to terminate the task 3 will be terminated and removed from the ready queue. And then next, task 2 will be in the running task and continue its execution. Then moving on to the context switch. Normally, context switch has one stack, but we wanted separation of concerns and no overlapping between variables. So we decided to divide this one stack into multiple stacks to make each task has own stack. And for example, here task 2 has its own context in the stack. And then when a preemption happens from task 1, stack pointer will be loaded to task 1 stack and will its context. And then when another preemption happen, task 2 stack pointer will go to where it's left off by loading its context. And that's because we saved the context during the first preemption. And then when it finished its context and execution, task 1 will have this stack pointer went to it again where it's left off and code execution.
So before we tackle how we did interrupts, we have to understand how OSIC defines interrupts. So by OSIC definition, we have category 1 and category 2 interrupts. In category 1, the user is unable to use any system APIs. However, in category 2, we give the user the ability to use system APIs like task activation, task termination, which would usually require the invocation of a scheduler. So normally what would happen is that we have a request handler, and upon firing the request handler, it would go to the service routine, which would initiate the interrupt in the handler mode. Now, let's take, for example, task 1, a preemptible task with priority 4. Now, during task 1 execution, if an interrupt got fired, let's say it's category 2 interrupt. Now, going on to the service routine, if the user chooses to activate another task, task 2 with priority 6, now we have two main options. We can either, upon activation, do scheduling, and this would mean that task 2 will take the CPU. However, it would be running in the handler mode. Now, the other option would be to actually disable scheduling inside the interrupt. However, upon doing that, task 1 would continue running, which defies our requirement of priority scheduling. So what we did was, instead of letting the request handler point directly to the service routine, we let it point to our own function where we save context, initiate the service routine. After that, we do the scheduling.
So let's talk about configurations. So before talking about configurations, let's understand how the operating system works. So initially, the operating system is like any program. It goes through a linker and it produces an executable file and object file. But how the tasks and the interrupts and events and resources are getting injected to the operating system, it goes through a generator. So AUTOSAR defines an XML template to go through a generator. This template defines the configuration of the system. For example, the priorities of the task, what the resources the task will need, or the function that the resources will point to. Then it goes through the generator. Then the generator produces the header files that get injected through the operating system. So the way that we implemented our generator is by using a tool called Jinja. So here on the left, you can see our template XML file which we implemented. As you can see, we can define the interrupts and the tasks and etc. And it goes through the Jinja tool, and Jinja serves as our generator. Then it produces the header files. And finally, the header files gets injected into the operating system, and the operating system gets executed normally.
And next, on how to use our OS, we have two main clients to our OS, basically the developer and application user. First, for the developer, he has to port our OS by writing a hardware code and Marcus function to be obeying with our OS. Secondly, for our application users, they have to do two things. First, configure the code. Application user should generate the configure code to generate our OS and be compiled with our OS, as well as define the tasks and hooks and interrupts and required functions to be able to work on our OS.
Now for the demo. So for the HSM demo, we decided to use three accelerators actually: the true random number generator accelerator and the encryption decryption accelerator. So for the HSM, we first activate the random number generator task. So when you activate it, we initial the value rand with 0, and upon true processing, the value the accelerator would generate actually a new value, which would mean that this if condition would work, and inside it we would activate the encryption decryption task. So as you can see, the random number generator actually generated a new number, meaning that we activated the encryption decryption task. So inside the encryption decryption task, we pass first a value, the word good, to the encryption accelerator with our own key, with the encryption key. And upon doing so, the encryption accelerator would actually generate a new value, which would be saved inside the out variable, as you can see. And after that, we're going to pass the out variable and our encryption key to the decryptor accelerator, which would eventually, if processed correctly, would give us the same word, good. However, we thought that this was not enough, which is why, to check portability, we have decided to port our own operating system on the STM32F303, a non-HSM core open source microcontroller that is used here by students in the university in the embedded lab course. So a quick overview on the demo itself. So first, we have the idle task, the default running task to keep the system up and running. First, we're going to activate task 0 using an interrupt, a push button interrupt. Inside task 0, we would declare a few variables, x and y, with the values 5 and 12. After that, we're going to wait for an event. So waiting for an event puts the task in the waiting state. Now, using another push button, which would initiate another interrupt, we would activate task 1, which would activate another task inside it. Now, after that, it would set event for task 1, meaning that task 1 would be moved from the waiting state to the ready state. Now, eventually, task 1 will take the CPU, and in task 1, it's going to do operations on the Z variable, which would be clear in the MX monitor. So MX monitor is a tool that allows us to monitor certain variables in our system and how our system behaves. So first, the system is in idle state. Now using a push button, now it initiated task 0, as you can see in the running task ID. Now task 0 will be put in the waiting state. After that, we use another push button to activate task 1, as you can see in the running task ID, which would activate task 2. After that, we're going to go back to task 0 since it is moved from the waiting state to the ready state. And eventually, as you can see on the right, the Z variable is now at 60, which means that our system operated successfully and did successful context and scheduling.
Now, to finalize our presentation, let's talk about empowerment outcome. So initially, we decided to have an open source project, but then we found out that the HSM is a confidential piece of hardware, cannot be published on the internet. So we found 3 solutions to this problem. The first solution was to publish first repo. The first repo includes an open source, including the software layer only on the operating system, excluding any hardware-related pieces of code. But we thought that if the developer will need to write his own hardware from scratch, why he wouldn't implement the software also from scratch. So we found another solution to have a second repo, an open source repo that includes a fully fledged operating system flashed on the STM32F3 Mac controller, including its hardware and interrupts, etc. And this is what we demonstrated our demo on. And finally, we have our confidential repo that includes the HSM implementation that will not be published. But how did we keep track of our requirements and all of that? We had a requirement matrix that collected our requirements from 2 documentation, the SWS documentation and the OSIC documentation, and we keep track of what we implemented and what we tested. And with that, we can say we satisfied around 86% of our requirement metrics. But how did we test this? How do we test our implementations? So we had two testing implementation. For the software only, we tested through GitHub CLI, which is a certain script we implemented on the GitHub that runs certain scripts, certain test cases on the software layers. However, when we shifted towards a more hardware implementation, we couldn't implement such implementation. So we shifted towards a more brute force implementation to test each test case on the hardware manually. And to conclude this, we can successfully say that we satisfied the modularity of operating system which we wanted, that can be scalable, and it can be changed without affecting any other components because it was modular.
Finally, before we end our presentation, we would like to thank our team working with Siemens, as well as our supervisors, especially Dr. Mohamed Shalan, and our committee, and end of all, thank AUC for granting us this opportunity. Thank you.